Okay. Good afternoon, everyone. Welcome to the third day of the CHPC NITheP summer school, and we're very happy to listen to the continuation of story by the Professor Zurab Janelidze. Zurab, it's your show.
Thank you very much, Ilya. Could you please just confirm that you can see my screen about...
we could see your full screen, so yeah, we can see your browser.
Okay, wonderful, thanks. So going to open the Blackboard for our use. So thank you very much to everyone who has been completing the quizzes and assignments. I've been trying to mark them. There might be a few still outstanding, and also I think these marks, don't take them too seriously. It's just a way to give you feedback how far you are from the intention. It's not to make any kind of judgment about your abilities, of course. Okay, we are at this point right here in the notes, where we're going to discuss variables in the context of Sophia. But perhaps before we start, it would be a good idea to maybe give opportunity to the audience to perhaps ask some questions if there are some things on which you are stuck. Since having a solid foundation is of course important for being able to continue well with whatever material comes. So if you're stuck with some concepts or material on this that we covered so far, please do ask your question.
Okay, Isak, you're welcome to unmute yourself and ask a question.
Hello, Prof.
Hello.
Yeah, good afternoon, everyone. Yeah, Prof, I wish you could help me understand the variables. Last time I couldn't join the last part of the meeting, so in today's quiz, I got a mark which I wasn't expecting that mark. So I wish you could take some time to explain, the variables to me. Thank you.
Yeah, we didn't cover variables last time. So we're going to start today's session with variables. So you didn't miss any of that. Okay, great. Then we can, I guess we can begin. I don't think there is anyone else who wants to ask anything.
Yeah, I think, yes, you can begin, yeah.
So, in general, in mathematics, variables are very important, right? So variables allow us to talk about things in an abstract way without being too specific. And of course, that's important for mathematics because in some sense, mathematics is the part of our knowledge which is abstract. When things become too concrete, the more concrete they become, the more we lose mathematics, and of course the real world around us is very concrete, and it took centuries for us to discover that there is actually some abstract mathematics behind this concrete world. Because variables are so important in mathematics, of course they will play an important role in the language of Sophia, which tries to express all phenomena of mathematics. And so we have to take care to properly understand how variables are used. And first of all, which Sophia expressions constitute variables. Let me remind you that we discussed this idea that Sophia expressions in general are sequences of symbols where brackets are placed correctly. But then they decompose into two types of expressions called statements and formulas. And these two types of expressions are mutually disjoint. You cannot have something that's both a statement and a formula at the same time. And so in this picture, variables fit in a very nice way. Variables will be special types of formulas. The definition is actually quite simple. It says that a variable is a formula that does not contain any brackets. So let's immediately give an example of this, maybe several examples to show when something will be or will not be variable. So, for example, this. Do you think this would be a variable? If you think that this would be a variable, say yes, please, on the chat. Okay, so we have quite a few yeses, and indeed that's right, because it is indeed a formula, as we know from our previous knowledge, and it does not contain any brackets, so it's a variable indeed. On the other hand, if as soon as I put some brackets there, maybe I put bracket here and here, we now still have a formula, but this is no longer a variable. So this one is a variable. But this one isn't. What about this? Is this a variable? It's not. It's not a variable already because it's not even a formula, right? Exactly, yes. So someone said in the chat that it's a statement. So it's not even a formula, so it definitely can't be a variable. So this is not a variable, we can say, not even a formula. So you see, it's not difficult to recognize variables in Sophia expressions. And here on this on these notes, we have an example of that. We see the picture here on this example. So we begin with, so this is another drawing of ontology of a Sophia expression. We see the first statement there. It talks about X, which speaks isiZulu and also speaks English. And then there is a statement that X speaks Chinese. And then if we draw the ontology for this, we notice that the first statement breaks up into synapses of two formulas, because the bracket right here, this bracket opens up and closes here. So this unit is together, and then we have another unit there. And because of that, sorry, I'm trying to delete this. Right, okay. So because of that, we have two separate formulas that are combined into a statement. And now we continue decomposing. I mean, so far, both of these formulas have brackets in them, so they can't be variables. But let's decompose them further. Here we have this formula arising from, okay, there is a mistake here on this diagram. No, sorry, there isn't a mistake. No, there is a mistake, yeah. The whole diagram is actually wrong. Sorry about that. Okay, let's do it right way. Once we are at this point where we have X, with X speaks isiZulu, and we also have this part which says X speaks English. I'm going to abbreviate that like that. What we have here is three statements, right? So this is the scenario where out of formulas we create statements. So the breaking down of that will be into X So there'll be 3 of them into X. So one formula X, the other formula is X speaks isiZulu, and the third formula is X speaks English. So the left-hand side is actually fine. This is actually correct. The mistake is on the right-hand side, where we have a formula X speaks Chinese. And so this is a formula. So its synaptical decomposition should produce statements, not another formula. So it decomposes into this statement. So this statement is turned into a formula by attaching speaks Chinese. And then it further decomposes, that one further decomposes into this one. So I will fix the picture here. I made a mistake there. There should be two-level decomposition for the right part here. Sorry about that. Okay. Now, if we look at the second line, where right here, we had we had 2 formulas, but both of them contained brackets, so they definitely were not variables. And then when we decompose them further, we have 3 formulas: this one, that one, and that one. So those 3 for the statement up there. Did I say that this thing is a formula, the first line? I should have said it's a statement, right? These are the formulas, the ones that I'm going to include now in green boxes. And on the other side, we had a formula already here. And then the next time we encounter a formula is this. So the candidates for variables are these 4: 1, 2, 3, 4. We will still check whether they're formulas, they're variables or not. But let's continue this decomposition further. So this one still decomposes as X, and then X with brackets, the statement of X, and then we have X without brackets. And here, similarly, we have this, and then we have that, right? And these ones are also formulas, of course. So 1, 2, 3, 4, and we have 5 and 6. Now, we did this ontology for the starting expression, which was a statement. And we find that possible candidates of what could variables be here are the ones that I marked with green. But now, in a variable, we can't have brackets. So this one is ruled out. This can't be a variable because there are brackets there. And also this one is ruled out. And then we're left with just these options. This one, that one, that one, and that one. And of course, all of these are variables, which we can also recognize because X is a standard symbol for a variable. And they're variables because they're formulas which don't contain brackets. And all these variables are the same variable X, in fact. Okay, are there any questions to this point? So we can say that the only variable in the thing we started with, in the original expression, is X.
I think there is a question from Isaac. Isaac, go on.
Yeah, hello, Prof.
Hi.
Yeah, so can you help? I'm not clear because looking at the X with the brackets from the previous lesson, we know that one to be a statement. But will you have to unbracket it before you can consider it to be a formula? I'm still not clear with that one.
Yes, statements. So statements are, remember, statements are things that have this structure: open bracket, close bracket, some expression in between, open bracket, close bracket, some expression in between, and so on. These are the things that are statements. And everything else is a formula. Does that answer your question?
Yeah, yes, please. But the X with the brackets that we have here, everything inside the bracket, we have X inside the bracket. So that's what I still know that one to be a statement. Not
Exactly. This is a statement. Yes.
Yes, please.
This is a statement. And then its synaptic decomposition is then just X without the brackets. And that is a formula.
Oh, okay. So you lay emphasis on the X.
Sorry?
What about inside the bracket? What about it is inside the bracket is what you have to lay emphasis on?
Yeah, this X here is that X there inside the bracket. When I'm drawing this X separately, what I mean is this part, which doesn't have the brackets.
Oh, okay. Okay. Okay, thanks.
Ilya, it tells me that my internet connection is not stable, so I do apologize if there will be a bit of disruption.
Okay.
Okay, so, but so far you can hear me well, right?
Yes, yeah, so far it's perfect.
Okay, that's great. So we actually have a tool, a little code, which we can use to extract variables out of an expression. So let's experiment with this now. So we can copy paste this into Spider. And in here, we can put an arbitrary Sophia expression. And then we can run this code. And the result of that will be that we'll have a list of strings, and each string will be a variable that Sophia found in the expression we gave. So we see here, according to this list, that the variables in this Sophia expression E, the variables are x1, x3, and x3, which appears second time. And we can recognize this x1 there, x3, and x3. Now, why isn't x2 a variable? Because, I mean, x2 on its own does not have brackets, so it could have been a variable. But the point is that if we do the synaptic ontological decomposition of this statement, right, we will never encounter x2 there. This bigger strict inequality sign together with x2 is one gadget that will be included moving up from x1 with brackets into x1 with brackets being bigger than x2. So let's actually visualize this. And then after that, I'm going to take a question from Pumelelo. So something like this, if I have something like this, right, synaptic decomposition of this would be, so the ontology of this would be that we have a formula, and then the next step will be a statement. Just might have to make my screen blackboard bigger. And then the next step after that will be x1. And you see, x2 will never get isolated in ontology. And that's why x2, although, I mean, x2 on its own, if we had x2 written separately, it would be a variable, but x2 is not a variable in this Sophia expression. So x2 is kind of seen here as part of the words like, did you know that, for example? I mean, we certainly do not want, did you know that, to be a variable, right? Pumelelo, would you like to ask your question?
Yes, thank you very much, Prof. Ask about the scope of a variable. Can we define the scope maybe as a variable has meaning?
Yes, we can, but we haven't reached the scope of a variable concept yet. We're building up to that concept. We haven't defined that concept yet in the lecture. So when we come back to that concept, maybe you can ask that question again, okay?
Okay, thank you.
So at this point, we're still learning how to recognize a variable inside the Sophia expression. So let's look at a couple of examples. I mean, if by the end of this lecture you're still not sure, you can always use this tool to confirm what variables can be found in an expression. But now let me ask.
Have we lost Zurab? Zurab, you're muted.
Ilya, can you hear me?
Yes, now I can hear you.
Okay, so it tells me that it's unable to establish secure connection to Zoom. I hope it's fine.
I also hope that's fine.
Okay, was I gone for a long time?
No, just for a few seconds, for a minute.
Thank you very much. So answering Monekiwa on chat, you're right, absolutely. In the expression that you wrote, x1 and x2 would be variables. And now let's look at this expression that I wrote on the board, but I think I'm not sharing the screen anymore, so let me share it again.
Yes, yeah, no, now it's happening, yeah. Okay, now we can see your desktop.
Great, thank you.
And the board.
Yeah, so let's see if we can correctly identify what are variables in the thing that I wrote on the screen. So you can type in chat the list of variables for this expression. So far, only one person answered. Maybe others could also answer. Thank you. Good. So that's absolutely correct. Z does not qualify as a variable because of the reasons we talked about earlier. Ontology of this would be, so this would decompose into, first of all, a formula. And you see why it is important to have this idea of ontology, because it helps us identify variables. So now we have an application of ontology. So this is a formula, and this would decompose into statements, and they would further decompose into formulas. And the variables, as we see, are just these two. Z is not there. Okay. So let's maybe do another example before we move on. What about this? What are variables in this case? Thank you, Joshua, for your code that would help us confirm the answer to the question. Exactly. So here the variable is just this one. Tasty doesn't get to be a variable because, once again, if we decompose this, well, first of all, we will have a formula. And then when we decompose this further into statements, we'll have this. And finally, let's see if it's finally or not. So we'll have apple here. And something interesting will happen there. So we have a statement, so we need to turn this into a formula. So this will be tasty, right? And when we try to decompose this further, we will just have this statement. And of course, if we try to decompose that further, we will simply have an empty character here. So we could actually say that it stops there. Empty string is considered as a formula, so we could actually decompose this further, but it's also okay if we don't, and we just leave it like that, because the empty formula itself will not have any meaning. And maybe we should remark that the empty formula will not be regarded as a variable either. Let's see if I didn't forget to remark that in the definition. You see, it says there, in Sophia, variables are non-empty formulas that do not contain any square brackets. So I think I forgot to say they must be non-empty in the beginning of the lecture, but at least it's stated here. Okay. We are very close now to be able to start proving things in Sophia. We just need one more concept, and it's the concept of the scope of a variable. And for that concept, we will come back to the example we started off with. So let's look at this example again, where we had this initial expression given this way, the thing that I'm going to enclose in blue box. Oh, okay. So sorry, that one was already. This should be actually down here. And what should appear up there is that enclosed in another pair of brackets. Okay. No, I'm making a mess now because I think I will just have to go to a new page. Sorry about that. Okay, let's go here. What I want is something with one more pair of brackets as originally written out in the lecture notes. It was like this. Let's check. Yeah, so you see that the X begins here with two open brackets, just like there. So we have basically two statements, right? So this is one statement, and next to it, there is another statement. Now the question is the following. This X here, which is a variable, is it the same X as the X here? In other words, if X represents a human being, where in the first statement here, we're saying that X speaks isiZulu as well as English, remember, when we put statements together, like these three statements, when they're placed together, the idea behind this is that we want to state all three of them. So we are stating that we are given some person X or some creature X, because we didn't say that X must be a human being necessarily. We are also given the fact that X speaks isiZulu, and we are given the fact that X speaks English. And because in each case we are using the same name X, it probably means that it's the same X that speaks isiZulu and English at the same time. But then all of that we have enclosed in a pair of brackets, right? And then we leave that statement and we move to another statement, which is its own pair of brackets inside which we find another X. And the question is whether these two X's are the same or not. So the person that speaks isiZulu as well as English, is that the same person who speaks Chinese? So what do you think would be the answer to that? The thing is that it's basically up to us to decide, okay, what rules to implement at this point. We could have assumed that every time we encounter X, we always mean the same X. But that's not a very convenient thing to do, because remember, in mathematics, you have a lot of times you have one formula, then you have another formula from a different context. And this formula might involve X, the other one might involve X, but you don't necessarily want to think of them as being the same X, right? You want to be able to take two formulas from, let's say, two different pages of a book, put them next to each other and read them next to each other. But now the fact that they have same symbols occurring, it doesn't really mean that they're the same number or a function. No? So we want to have this ability to distinguish variables even if they are represented by the same symbol. And having that in mind, when the X that appears here as a statement is enclosed in another bracket, this one specifically, the identity of this X remains confined within those pair of brackets. So this person X will stay to be that person only inside this area here. And as soon as we leave these brackets, right, X becomes free to represent anything else. So in our example then, this X and that X don't have to be the same. However, these X's, this one, and that one, they must be the same. Why? Because of this one, but now we're going to explain this a bit better, okay? So let's explain this a bit better. To explain this a bit better, once again, we need to look at the ontology of a statement. Perhaps this is a good example again. It's just that this right-hand side part had a little mistake there. So let me fix that by copying this and then pasting here, and then correcting the right-hand side before we continue on with this. So there we have the picture from the lecture notes. Maybe we need to make it a bit smaller. And I'm just going to correct this a little bit here. So we should have had first, oops, sorry. We should have first had X there with the brackets, and then without. So now it's correct. Now that's a very good question from one of you who sent it to me as a private message. The question is, what is the purpose of this X here? I think that's the question, right? It has two purposes. And one of them will be exactly to pinpoint identity of various different X's. So according to the rule that I just spoke, this X here loses its meaning outside these brackets. In other words, that X here, which is the same as this one, will only, we will remember what it means only inside here. And as soon as we step out from that block, we no longer remember. So that means that had this x there, had that x not been there, these two x's would have been possibly different. There's no way to see that they're the same because they're separated from, they're separated by these brackets, okay? On the other hand, with that x there, such separation no longer takes place. I mean, these two are still separated, but they're both connected to that one. So when I have a variable, now the definition goes like this. When I have a variable, the scope of that variable, in other words, the part of the expression where that variable retains its value, its meaning, is the block on the ontology. It's the block immediately above the variable. So for this variable, it will be this block. So you look at the ontology, you find your variable, and then you see what's immediately above it, and it's this. So that block is immediately above this block. And now this tells you that all the x's you will find here, all the x's that you find here, right? They will be the same x as this one. So that x and this x will then be, of course, the same as that. On the other hand, if we look at the right-hand side, the block immediately above the variable is, of course, this. And so x has only has a meaning right there. But this does mean that there is a separation between the scope of that x and the scope of this x, right? So these two x's, this one and that one, they need not be the same because the scope of one is this and the scope of the other is different. Their scopes don't overlap. Let's now look at another example, again from the lecture notes. Here is another one. If we look at the variables there, x, y, and z, and x and z, right? So the scope of x is the block immediately above it. So it's this block. So you see that this x here and that x there, they're far apart. So they don't have to be the same x. Okay, let's look at some questions. Go ahead, please. Otto, ask your question.
Hi, can you hear me?
Yes.
Sorry, I asked the question, I sent it to you. I just wasn't sure when's the right time to ask questions. My issue is if we say X speaks Zulu and X speaks English, right? And then we put those two under brackets, then we know that the X, the scope of that X is the same thing. The X that speaks Zulu and the X that speaks English is the same thing. And that the X that speaks the Chinese is different because it's not in the same set of brackets. So my question was now, what does the X on the side all the way to the left have to do? Like, how does it relate now to the same syntax that we've been using? Because now it's in its own set of brackets, but it's within the bigger brackets. So does it mean that it's still part of the X that speaks Zulu and English, or is it a different X entirely, but it's within the same brackets? I don't know.
Thank you very much for that question. It's a very good question. So it is because of this X that these two X's are the same.
Ah, okay. So
without this X, the scope of each of them are just these, and you see they're separate scopes. Because remember, the scope is just one thing above. So if this X hadn't been there, this X and that X wouldn't have been the same.
would you have still put it in the same brackets, or would you have?
Oh, I'm just saying that imagine I erase this part, okay? Everything else remains the same. I just erase this part. Then the two x's there and there, they don't see each other anymore.
Under those circumstances, what would having the x that speaks Zulu and the x that speaks English in the same brackets mean? Would that even mean anything?
Yeah, for some reason they are grouped together and x is Chinese is grouped separately. That doesn't mean that the x's on one side are together necessarily.
Okay, all right.
Okay, great. Then there is a question from Isaac.
Hello, Prof.
Hello.
I would like to know from the expression that we have down there, can we say now we have two variables for that expression? We have one x at the left-hand side and one x at the right-hand side.
Yes, we can, but we should be careful. What do we mean by a variable? So there is one thing to talk about a variable, the other thing is to talk about occurrence of a variable, right? So you're right that we have two free variables, so to say. You're right, but then if we start talking about the occurrences, then there are four occurrences, right? Actually, three occurrences of one variable and one occurrence of the other. So this Sophia code, when we ask Sophia to list all the variables with this code, she will list them as many times as they occur. So the scope, she doesn't take, she doesn't care about the scope with this specific function of vars.
Okay.
But we do have 2 degrees of freedom only. You're right. So we only have 2 degrees of freedom here, this x and that x.
Okay, thanks.
And then there is a question from Evander.
Hello, thank you. Please, I'm a bit confused.
Hello, it's a bit quiet. Maybe you can try to speak louder.
Hello, please, can you hear me?
Yes, now it's much better.
Yes, so I'm a bit confused with the statements, formula to statement stuff on the right-hand side. So I understand that the first statement we have is the first box, which is this one where you are up above.
Yeah.
No, above the very first one.
Yeah, the top one, right?
Yes, it's a statement.
Yeah.
Right. Yes, and the second line is a formula.
Not quite. So here, in this specific example, you see we don't have any other characters. So in this specific example, this part is a formula, but this one is still a statement.
Okay, so that makes the whole line a formula, right?
The left one or the right line?
Like the whole line.
No. The whole line is nothing.
So with the ontology, it doesn't matter what it's supposed to be, because I was thinking that since the first line is the statement, the second line, the whole of the second line should be a formula. Then the next line should be a statement.
No, so in those cases where we have brackets like this and we have more brackets like this in there and no other characters, then it's a kind of abnormal situation where synaptic decomposition produces from a statement another statement, which would be this.
Oh, okay. The reason why I'm saying this is from the previous lecture, I understood that when we are doing the ontology, we move from maybe if you have a formula, you move to a statement, then you move to a formula.
Yes, you're making a very good point. I remember I said it that way, and I forgot to describe this exception that in cases like this, when the brackets are just so when a statement is simply enclosed in a bracket, in cases like this, it's a kind of abnormal case where that rule breaks.
Okay, so in that case,
I apologize for that. I should have said it already the other lecture. So there is a case when the rule breaks.
Yeah, so I got confused because I was trying to change that part to a formula, and from what I had and what you got was quite different.
But let me also add that even if it was a formula, still this thing and that thing should be separate from each other. We shouldn't think of them together being a formula.
Okay. All right.
That's why we have these blocks to distinguish. Yeah. Okay.
All right. Thank you very much.
So thank you so much for your question.
Sorry, Zurab, there is a question also in the chat. Can Sophia show scope?
There should be a function in Sophia to do that, because scope is used for proofs, but I haven't prepared that function for our use. So at the moment, I would say no, but I will think about it afterwards. Maybe I can easily extract a function that's already implemented in Sophia, or maybe you would like to write a program for that as well. Okay. Okay, great. So let's move now to the actual proofs. We will, in the process of working out with proofs, we will have one more chance to clarify for ourselves what the scope of a variable is and so on. The first proof that we're going to compose is the thing described here. So what I'm going to do, I'm going to, well, we already have the output shown here. So I'm going to simply start off by just discussing this output as a kind of starting off from an example, and then after that I will say some general things about this. So let's take this picture and let's explain this. Oh, that's not good. Okay, that doesn't work. Maybe we leave it like that then. So first of all, we should say what is a theorem in mathematics and what is a proof. A theorem is a statement, something that we claim to be correct. And in the Sophia language, of course, because of that idea that we claim something to be correct, a theorem will not be a formula, but rather it must be a statement. Let's look at this specific theorem, this specific statement. And let's explain what is it trying to say. This colon here will have a very specific meaning. Okay, there we are. Basically, colon in Sophia is just a symbol for implication, something that you would have seen before as this. Okay, there's a question from Otto about something being a valid statement. Let's check quickly. Yeah, that does look like a valid statement indeed, yes. And in that statement, X and Y, the scope of X and Y is the entire block, right? Because that statement is a synopsis of X, Y, and the rest. And so the block immediately above it will be the entire statement. So it's the same X and the same Y that we're talking about when we talk about whether they're from Chad, Uganda, or whether the sum is from Africa. It's the same X and Y. Thanks, Otto, for that example. So to say that one thing implies another, we use colon. It's just one symbol that abbreviates this implication. But what does implication mean in general in logic and in mathematics? I mean, we use this symbol a lot in mathematical text, and sometimes it is even used in an incorrect way. A very simple example of what it means is the following. x equals to y, so I'm not using Sophia anymore, just ordinary language, x equals to y and y equals to z implies x equals z. So what is this saying? This is saying that, this thing is saying that if both of these are true, both x equals y and y equals z, so I actually need to have brackets here. If both of these are true, then this must be true as well. So surely you will agree with me that if x is the same as y and y is the same as z, then x will be the same as z. It's a very trivial thing to say, right? Okay. So implication is a kind of consequence, right? The logical truth of one thing gives as a consequence logical truth of another thing. That's the idea behind implication. So if anyone is not certain, if you haven't worked with mathematical implication, maybe this is the right time to say that. We can then do more examples on implication. But if you're more or less familiar with implication, then we can move on. Is there anyone who would like us to do more examples to explain what the meaning of implication is in mathematics? I'll just give one more example. X plus 3 equals 5 implies x equals to 2. In this case, we also have the other way around. X equals to 2 implies x plus 3 equals 5, right? But in general, we might not have the other way around. For example, here we don't have it the other way around because, okay, x could equal z, but it doesn't mean that some arbitrary y must be equal to both of them, right? So it's a very good example of an implication which only goes in one direction. Whereas in this other situation, implication can go both directions. In mathematics, we usually use this symbol when the implication can go both directions, but in Sophia, we haven't implemented yet that, so we just use one-sided implication. Yes, Pomelelo?
Okay, thank you, Prof. So before we use implications, don't we have to use like self-evident statements, like postulates, before we can establish the truth of a statement?
Exactly, and so in this example, the self-evident statement, well, it could be self-evident or it could be an assumption we make, right? So like, for example, here, we don't know what x is yet. We're saying, assume that x plus 3 equals 5. So it's not evident because we can't check this because we don't know what is x. But if we believe that this is the case, then we can conclude, oh, then x must be 2. Does that make sense?
And those assumptions, what informs them? Basically, do we just make any random assumptions? Is there like a framework we generally use?
These assumptions will come from real life problems or from some mathematical exploration we are doing, right? For example, if I tell you that I have some number of apples and if you give me 3 more, then I'll get 5, right? And then I denote the number of apples I have by x, then I'll get this. And so this assumption will then come from the information I gave you about my apples. And then from there, you will be able to conclude that, aha, therefore I had 2 apples. Does that answer your question?
Yes, thank you. Okay,
great. So when we make some assumptions, it's always because we encounter some phenomenon, whether in real life or in mathematics, where we seem to believe, we seem to have evidence that something must be the case, like x plus 3 being equal to 5. And then we want to see what conclusions we can draw from there. Yes, Ilya?
Sorry, yeah. But I mean, when you're saying that x plus 3 is equal to 5 and we imply that x is equal to 2, this is under assumption that the plus is the normal plus operation over the numbers, yes? Because
exactly. Yes.
And one more stupid question, you know, kind of like with x plus 3 is equal to 5, it's okay, but with the transitivity, if x is equal to y and y is equal to z, we assume that implies that x is equal to z. Do you know examples of non-transitive systems?
Where equality is not transitive?
Yes, where this wouldn't work, yeah.
Yeah, so this brings us to the question, what is equality? You could have another relation instead of equality. For example, you could have the relation that, let's say, x equals y means not that they're equal, but means something else. So let's say it means that the distance between them is 1.
Okay, good. I see a point. Yes, of course, yes. If between the 2 points, I can find the 3 points. Yes, between distance will be larger than 1. And of course, okay.
Yeah.
Interesting. Thanks.
And so in general, this property of transitivity for an abstract relation is a very important property in mathematics. And it is encountered in several different types of applications as well. And equality is one of those that's transitive. And it turns out we can prove that. So we don't have to assume this as a kind of definition of equality. It turns out we can prove that equality is transitive. And this is what we're going to do right now with Sophia. Because in fact, what I wrote here is just nothing other than ordinary mathematical way of writing this. And I'm going to explain why. So let's try to build, yeah?
So there is a hand from Manikiva.
Yes, Manikiva.
Yeah, thank you very much, Prof. Suppose now we want to prove that a statement is false using Sophia. For example, if we have a statement and we say that x plus 3 equals to 5 implies that x is equal to maybe 3, and we want to prove that statement is false. How do we do that?
Now, when you want to prove that something is false, it means to derive a contradiction. Do you agree with that?
Yes, yes.
So will we be able to derive a contradiction from the fact that this implies that? The interesting thing, Monikiwa, is that this implication is not false. It's correct. Okay, never mind. I take it back. It's actually false. And let's see if we can derive a contradiction. So let's take, well, first of all, we need to decide whether we mean this to be true for every x or not. Are we claiming that this implication is true for every x or just for some x?
Well, the basic statement as we are given would prove that by
so the basic
means,
statement has x a variable, right?
Yes.
And we need to know what x represents. What can x represent?
Yes.
Anything or a specific number?
Well, it can arbitrarily
okay, so if it can represent anything, then from this line we can conclude this line, right? So if x can be anything, it could also be 2, right?
Correct.
Now 2 plus 3 does equal 5, doesn't it? So we can write it separately. 2 plus 3 equals 5. Do you agree with that?
Yes.
And now we said here that if 2 plus 3 was equal to 5, then 2 must have been equal to 3, right?
Yes.
But 2 plus 3 is equal to 5. So therefore, we've concluded that 2 does equal 3, right?
All right, I see it now.
And this is the contradiction we were looking for. So we were able to conclude from this initial assumption something that's a contradiction. And that's how we prove that something is false, by concluding on contradiction.
All right, thank you. But I was trying to ask if you can write a code on Sophia using Spider, of course.
Exactly. Yeah, we will be able to prove, we will be able to replicate this argument we gave here on Sophia.
All right, thank you, Prof.
But we are still, we need a few more things to develop before we arrive there. I mean, what I'm saying is that I will not do it now. I mean, I will not do it today. Okay. So the way we can do it in Sophia is to introduce something like this. I put this bracket so that it's not a variable, and this will be our universal false statement. And whenever I want to derive a contradiction, I will be trying to derive this. So for instance, because 2 is not equal to 3, we can agree that 2 equals 3. From this, we can derive false. And now because from here we derived false, then the original thing was false. So being false means to be able to derive false. You can think of it like this, that something is false when you can derive from it some absurdity. So you can think of this thing as some kind of absurdity. Just one shorthand notation for a universal absurdity. We will come back to this discussion about false later on next week. It's a very interesting topic, actually. Coming back to transitivity of equality, I want to explain now why does this Sophia expression capture the idea we had here. So let's begin with usual transitivity and try to turn it into Sophia expression. So the usual transitivity says this. I mean, the usual transitivity of equality says this. And when we try to write this in Sophia, we will be inserting these brackets, which we already know why, because we want to think of these x and y as variables. Otherwise, they wouldn't be variables. So that will be the first step. And now I want to state this, right, along with the other one. So I naturally have these brackets arising here as well. And because I have the two statements put next to each other, that captures the idea that I want to combine x being equal to y together with that, right? So when we state two things next to each other, that's stating that both of them must be true. Now, all of this is our assumption, the thing that goes to the left side of implication. So then we put the implication symbol and we put the conclusion, which will be again of a similar style. It's all good, except there is one problem. At the moment, the scope of this x here is what? So if I do synaptic decomposition, that's a statement. This is a formula. Then it decomposes into further two statements, right? And then decomposes into, so you see, this is my variable. Immediately block immediately above is this. So the scope of that x is just this. This x, we don't know that this x and that x are the same. We want to fix that. How can we fix that? Remember how we, in the other example, how we had this phenomenon where we had this x that was binding things, like here. We had this x here that was binding the values of these two x's. So that's what we want to do there. But maybe someone wants to suggest. So place x in the leftmost position. Exactly, yes. Well done, thank you, yeah. That's what we will do. Oh, I've lost, okay, here it is. We will put the x, we will state the x. And we will put it in the leftmost position. And then the scope of this x now will be the entire thing. Why? Because if you think about it, the synaptic decomposition of this is what? It has, it's a formula, right? Made out of statements, right? It's made out of two statements. And I think I'm realizing now that I didn't explain the scope as well as I should have. So the two statements here we'll have is this. The other one will be this, right? And then when we decompose this further, we will have, so this is several formulas put into a statement. So it will be x x equal y, y equals z. And here we will have x equals z, right? And then decomposing them further will give us, but we don't need to decompose further. We just need to look at this x here. So you see, I mean, we said before that the scope of x is going to be the thing immediately above it. But that's not completely correct. So we want to skip one step because we want to arrive to the next formula. So the scope of this x, when it's inside a formula, will be not something immediately above, which is this, but it will skip that step. It will be this one. Okay. This is bad because I don't think that I explained it correctly in the beginning. If we go back to the other example, in fact, already here I felt that I was doing something slightly wrong because of that idea of skipping one step. The scope of this x here is not necessarily just this, but it's that whole thing, this one, which makes more sense. Since if I had another x there, I would want this x and that x to see each other because they are part of the same formula. Now, the question is, when do we skip and when we don't skip? Because here on this left side, if here I skipped 2 steps, right? If I skipped 1 step, then I would arrive to the whole thing, and then I don't want that to be the scope of x. The reason why I have that phenomenon there is because this was this awkward situation when in the synaptic decomposition, I have a statement, and then right below I have another statement. It is because of this that this confusion arises. The rule for skipping is that I can jump over one statement, but then where I land should be a formula, not a statement. So here I can't go, the scope of x can't be that, because then I've jumped over 2 statements, this one and that one. Whereas in the other example, I only jump over 1 statement. So when I go from here to there, this thing is a formula. So I only jumped over 1 statement, not 2. Okay, so I apologize for that bad explanation on that other example. That's why it's not always good to explain things on an example. You miss out some other cases. Great. So by putting this x here, we are binding the values of these 2 x's, and now we want to do the same thing for z, right? So we will put not just x, but we'll also put z. Maybe I'll do it on a separate line. I left a space there deliberately because I also want to put a y there. Let's see why I need to put a y there. So if I go back here, what is the scope of the y's? I do certainly want this y and that y to be the same, right? So if I decompose this further, this decomposes into x and y, right? And then they decompose into x and y. And the same here. This should be yellow. this decomposes into the statement y and the statement z, and those decompose into y and z. And now let's see what our rule tells us. So this is the variable. Okay, I'm interested in the y variable. This is the variable y. The scope is supposed to be this, but I can skip one more step if I arrive at the formula, and I do arrive at the formula here. But I can't go further because this is again a statement. So then I would be including two statements in my skipping. So I stop there. So the scope of y is just this. Similarly, the scope of this y, the other y, is just this. So these two y's, they don't see each other. We want to bind them as well. And that's why we want to include this y there also. The end result is a formula, but we want it to be a statement if we want to claim that it must be correct. So we put everything in brackets. This way we turn it into a statement. And then this becomes exactly what we had on the picture here. Now let's see how to prove that. An interesting thing about Sophia is that, the software is that you will not be able to input the theorem. You will only be able to input the proof. And then Sophia will figure out, after you've inputted your proof, what you have proved. So Sophia will put the theorem for you. It will construct the theorem out of your proof. This is good because it means that you will never make a mistake. So if you do have a mistake in your proof, you will know that there is a mistake, because then the theorem that Sophia will output for you will be not what you expected. Okay? And this is one way in which now Sophia becomes a proof assistant, because she now helps us to validate correctness of our proof. So if my proof has a mistake, it will be proving something else or nothing, and then Sophia will figure out what it's proving, and we can trust her because, as far as we can trust that the one who coded Sophia did the right thing. Yeah? So to construct this theorem, we will be constructing the proof, as I said, and then Sophia will state the theorems. And the proof is very short, and I will explain each line of this proof. This is the entire proof. So let's go here line by line. The first line is, of course, very simple. We just load the Sophia module. This has nothing to do with the proof. Second line, we say P equals Sophia.prop, and then we give a name to this, which we call equality is transitive. At this stage, what we've done is we've created a mathematical proposition. So this prop here stands for proposition. A mathematical proposition is a mathematical statement that could be seen as a theorem, something we want to prove, or it could be seen as an axiom, something we don't want to prove, we just want to use this as one of our basic assumptions. So when we input this line in Python, what happens there is that a proposition object is created in the mind of Sophia. It has no information in it at all yet, except the name. So it only knows what it's called. The next step is to start building a proof for, start entering a proof, and this will be done line by line. And then at each step, Sophia will be telling us what the corresponding theorem is. So the first line of the proof, which is written out like this, P dot A, and then in quotes here, we put this ingredient. So who can guess what happens with this line in the proof? It's a very unfair question because it's difficult to guess, but maybe one can still guess. Let me take you back to apples.
There is suggestions in the chat. There are suggestions in the chat.
I see, but I don't see the suggestions.
Assumption?
Exactly, yes. Yes, so it's an assumption. Okay, I lost my track now. It's an assumption. Remember what we're trying to prove. We're trying to prove that if we are given three numbers, x, y, and z, and we are given the fact that x equals y and y equals z, given all of this, we want to conclude that x is z, right? So we want to assume that x is equal to y, assume that y equals z, and from this we want to derive that x equals z, right? So this line of the proof is just the assumption line. We're now telling Sophia, let's assume this is so. Let's assume x equals y, let's assume y equals z, and let's see what we can derive from there. Now we're going to see what happens when we input this line. So I'm going to copy paste this part, only the three lines so far. This is the output. We already have a theorem called equality is transitive. I hope you can see this. Maybe I can I make it bigger? I'm not sure how to make it bigger yet. Oh, view. Yeah, it's probably not so easy to make it big. And now I don't have much time either for the lecture. So if you can't see this, please tell me, otherwise I'll continue. We have the name of the theorem. And something interesting happens here. We have nothing. We have just open bracket and close bracket. So that open bracket and close bracket is an empty statement. It's a statement that says nothing. You can also think of this as universal truth, because if I say nothing, then I'm not lying. So I'm not saying anything incorrect, right? And we've got that statement there because that single line that we entered into the proof doesn't prove anything yet. So far, Sophia tells you, with just that line of proof, you've proved nothing. That's basically what she says. We have then the name proof. That's where the proof begins. And then we've got this thing we assumed. And then there is some very interesting symbol here. We will come back to that later. What is the next line? In the next line, we have this RS, which is short for right substitute. And then we have some parameters. So what we're going to do is the following. From this equality and from that equality, we want to derive that x equals z, right? One of the rules for derivation in mathematics is substitution. If you know that if two things are equal, you can substitute one with the other, right? So what we want to do is to use this rule of substitution, which is a very basic rule in mathematics, to prove transitivity. And indeed we can, because we could take, I mean, knowing that y equals z, right? We could take now this expression, and in that expression, we could substitute, replacing that y there with the z, because they're equal. That's what we want to do. The first parameter here tells us the equality that we're using for substitution. In which line of the proof does it lie? We only have one line of the proof, so that's why we have number 1 there. The second parameter tells us the place where we're substituting in this expression. In which line of the proof does that thing lie? Well, it's still line 1 because we only have one line in the proof. This tells us which of the variables in that line we're going to replace. We only have one variable, but if we had 10 of them, and maybe we only want to replace 5 of the y's with a z and leave the other y's there, we would just then have, in that case, we would have, let's say we want to replace first, second, and fifth y with a z and nothing else. Then we would enter parameters like this. So it's basically the list of positions of y's that you want to replace. Okay. Next parameter is this. This next parameter is attached to the first one. This one tells us in that line, which is line 1, the equality that we're going to use for substitution, which position does it have? Position of a statement is, in a statement, position is given by breaking down your statement into these atomic ones and then numbering them. So 1, 2, 3, 4, 5. So the equality we're using for substitution lies at position 5. That's why we've got 5 there. Now the expression inside which we're substituting lies at position 4. That's why we have 4 there. When we tell Sophia to do this, what she will do is she will take this equality, it's right substitution, which means that she will take the right side of this equality and she will insert that in the expression where we wanted to do the substitution, replacing the first occurrence of y with that right side of the equality. So she will take this z and plug it in here. And then she will write down on the next line of the proof the result of this substitution. So let's see how that happens. So I'm adding this substitution line, running it, and we see that now we have an update to this theorem. We now have this, which we got from there by replacing y with z, as we originally instructed Sophia. So you see, I'm not even telling her what the second line of the proof should be. I'm only telling her how to get it. It's a bit like this. Imagine that you want to play chess, but your hand is trembling. Maybe you have some disease and you can't control your hand. So your hand is trembling and you're afraid that you will make an illegal move because you will accidentally put your piece somewhere else. Then you get an assistant, someone who is physically much better than you, and you tell this person, I want to move with that piece according to the rule that I am allowed to make a move. And then the person makes the move for you. So we will be telling Sophia what rule of logic to use to get the next line. We will not be telling her what the result of applying that rule should be. She will be figuring this out for us. And once again, this is how she will be assisting us with the proof, because maybe we would have made a spelling, a syntactical error if we had to write this whole line out ourselves. There is a question here. Why is the substitution not at position 4? So there are two things. One is the equality we use for substitution, which is this equality, and the place inside which we are carrying out substitution, which is this equality. So at position 4 is the place where we are carrying out the substitution, but the equality which we use for substitution, for interpreting what should y get substituted with, is at position 5. Does that answer your question, Otto? Okay.
So can you please
yes.
repeat
Yeah, so there are two things.
What you just said? Can
there are two ideas. So one is where are we doing the substitution, and the other is what substitution we're doing, right? We are carrying out substitution in this part because we'll be replacing this y with something, right? But then there is also information of what will we be replacing y with, and that information is given by this part. This tells us we're going to replace y with z. This is the place where the replacement will happen. Does it help?
Yes, it does. Thank you.
Hi, hello.
Hello.
So is the syntax that, I guess in this case, the first sort of operation is the one where the substitution will take place, or whatever operations? Is that just the way Sophia works? That whatever comes first is going to be the thing that's getting done, and then whatever happens afterwards is what's supporting it. I don't know if I'm...
Yeah, so it's general to extract such a general rule. It's difficult to extract such a general rule, and that's why we have help function. So for each specific command, but there are not many of the commands, so it's not difficult to remember them. So for each specific command, there are rules. So if we look at this table, the right substitution is, where is it? It's here. And on an example, it gives you what it does. It explains to you what it does based on this specific entry. So you just have to look at this table, and for each command, you will see the meaning of the parameters. Basically, these commands are rules of logic, which can be used for deriving anything in mathematics. And it's amazing that we just need so few of them for anything. And we will also need axioms, of course, but as rules of deduction, we just need these rules. Okay. Okay, so there is one more line we need to add to the proof, and that is wrapping up the proof altogether. And that's called synopsis, and it doesn't take any parameters. What it does is that now it says, I've assumed this. I mean, what we've done so far in the proof is I've assumed this. From that, I was able to conclude that. And now I want to tell Sophia, look, I've assumed this and I concluded that, right? Therefore, that assumption implies the conclusion. So the synopsis rule is for Sophia to say, okay, since you assumed this and you were able to conclude that, therefore you've proved that the assumption implies the conclusion. So then the last line is exactly the theorem we were looking for, right? And just with couple of more minutes left, what these brackets do, these vertical brackets, if I show it here, the opening of the vertical bracket is assumption. So let's say assumption was some alpha, okay? We carry out computations and we arrive to conclusion. Let's say conclusion is beta. Now I want to step out from my assumption. I don't want to assume alpha anymore. I want to summarize what I've done. I step out, I say, okay, I've proved alpha implies beta. So this vertical bracket keeps track for me whether I'm under some assumption or not. If I've stepped out, I would have stepped out from that bracket, then I don't have any bracket anymore here. But we will talk more about this next week. So these two characters, right, in the first and the second line should be seen as forming a vertical bracket. Okay, so just to end off, I think there is some activity on Moodle, right? Is it okay, Ilya, if I take just a couple of more minutes?
Of course, sure.
Thank you very much. I'm sorry, that's because I was late. Otherwise, it's just the 5 minutes that I was late that I need. Oh, we still have Friday. I forgot about that. Sorry. Yeah, I forgot we still have Friday.
Yes.
So
Friday morning.
Yeah, exactly. Friday morning. Yeah. So the next is, I mean, there is a quiz for today. That's just the understand the scope of variables. And then for Friday, the assignment on Friday, on 17th of February, which is for tomorrow, actually, the assignment will be to get Sophia to compose this proof. And you see, it's very similar to what we did. It just has more variables. So we say x equals y and y equals z, and z equals t now should imply x equals t. So you have to just add a couple of more steps, repeating the substitution to arrive to now x being equal to t. So just by understanding this specific proof, you should be able to carry out the other proof as well. And I will be very interested to see your attempt there. If your attempt does not give you in the line right below theorem, I mean, it should give you exactly this statement. If it doesn't, it means you haven't proved it. So basically, Sophia will tell you if your answer is right or wrong by showing you what you have proved in your proof. But even if you haven't proved it correctly, still submit it, because then I will have a look at it and I'll tell you where did you go wrong with your attempt. Okay, I think I will end here. If there are questions, I'm happy to answer. Otherwise, we can continue on Friday.
Okay, it doesn't seem to be the case that there are any questions, but there were quite a few questions during the presentation. So it's my pleasant duty to thank Zurab for a very nice and interesting talk. And we're all looking forward to hear the continuation of the story on Friday morning. And tomorrow, we're going to hear the continuation of the story about the bioacoustics and statistics in R. Thank you very much.
Thank you very much. Thank you, Ilya. Thank you, everyone. Bye.
Bye-bye.